would like to welcome everybody to today's CISL seminar. Thanks for joining us in person and online. We're really happy to have Dr. Thomas Huang here from the NASA Jet Propulsion Laboratory. His topic today is open source framework for Earth system digital twins. And a little background on Thomas. He's a group supervisor at NASA Jet Propulsion Laboratory's Instrument Software and Science Data System section, and the strategic lead for interactive and analytics for the National Space Technologies Applications Program Office at JPL. And Thomas is the NASA principal investigator for the Earth System Digital Twins and system architect for NASA's Sea Level Change portal, as well as lots of other great activities over there at NASA. And he's a big promoter of open science and open software, which we really also appreciate here in CISL. So thanks very much for joining us today, Thomas, and we look forward to your talk.
Cool. Well, thanks for having me. And I was telling several of you when I was having lunch is I tried to make an excuse to come back here because this is such an awesome place, right? So I was preparing for my talk, and the first thing I pulled is like, this was the last time I was here. It was 2016. That was with Steve Woolley. And he gave us the tour of this place, and for a moment there, I really want to work here because he has such an awesome backyard, the view, right? But that was the 2016 is the project. Back then it was called DOMS, or Distributed Oceanographic Matchup Service. Now Tom is on this, the CDMS, Cloud Matchup Service, right? Right. So this is the predecessor of that project. So we had the privilege of having a first team meeting here, and that was the regional team. So Steve and Wah were the primary NCAR representative on the project. So obviously the project's been very successful because now we have a follow-on. And again, it's been 7 years. I still enjoy the view as I'm coming up here to my Uber. So a little bit about me. I've been in JPL for a long time, since 1995, that's a fact. So these are some of the projects I worked on. I've been developing software for planetary to earth science, and now do a variety of big data analytics solutions. Some of the software, I was kind of a little bit bragging to the team earlier. Some software I designed back for the Mass Pathfinder is still being used today. And it's crazy, but the whole point is the software is being able to extend and evolve over time by different generations of software engineer, providing core capability for near real-time data distributions. So yes, JPL is a very fun place, and that's why I'm in there. I've been forever. And as Doug mentioned, I'm a big open source advocate. So to prepare this talk, I also go back and start looking at when did I make the first contribution to the open source world? Everybody use open source software, right? But when did you actually contribute, right? So I actually managed to find the very first piece of code that I contribute to open source. That was more than 20 years ago, and it's still up in the internet, and it has my name next to it too, on that line of code that I wrote back in 20-some years ago. And that was to fix an issue with Kerberos. And some of you probably know what Kerberos is, and that was for Apache web server authentication. And of course, decades later, there are about over 30 softwares from JPL that actually I'm responsible for open sourcing it. So those little tape on there, these are the approval letters I get for you're free to open source this stuff, right? So yes, I am a big fan of open sourcing software, but it's not just so that I can get more liked on LinkedIn or Facebook, but it's really, to me, it's the only way you can further or enable or mature a solution is actually you open it to the rest of the world so people can help you improve it. So I can do other stuff like being a GS. So the key, right, to climate, especially for climate research and understanding, is about sharing our knowledge and reusing our technology and really promote this idea, right, collaboration. No one can have all the solutions, right? But I think collectively we can actually get a little bit better at it, right? So the first thing that we did very interesting over the last couple of years is this what we call the Analytic Collaborative Framework, that what AIST or NASA Advanced Information System Program calls it, which is a harmonized platform where you have one place where the data, observational, like satellite in situ, and model data, all in one optimized analytic environment. And the user can just work with those data without having to replicate or doing, because majority of our time, guess what? When we're doing data analysis, is data wrangling, right? Subsetting the data, regrading the data, right? And all that crazy stuff. And usually you have postdocs to do that for you. But then it's ugly because you use that data set, and then next person uses the same data set, they probably have to do the same thing again. It's like we have to pay the same process over and over again. So the whole idea about ACFs is really say, well, let's not do that, right? Can we have this optimized environment where we can have one stop where you can quickly look at and analyze this data and play with this data without having to go through those hoops. And it's also encapsulate the computational environment, so you don't have to know is this running on the cloud or on-prem. The whole point is always all based on API basis rather than terminal based, right? Log into a certain cloud environment. So the solution we created, it's been open source for a while, right? So just show you the timeline. This project is actually an Apache project. It was started in 2011 when NASA was trying to figure out what to do with cloud, and we were testing the Nebula cloud. I'm not sure anybody know about Nebula cloud. NASA was trying to build a private cloud in a big Craig in Ames. That's the birth of OpenStack, by the way, if you look at the history book. But we started building parallel analytic since 2011, and that was using Hadoop and point cloud, right? And since then, right, we've been evolving our architecture, and in 2016, we engaged Apache Foundation, and we actually donate the software completely to the Apache Foundation. Now the software is open to community, but then we have different projects contribute to that solution. So this is why since 2016, we're still evolving this solution, and it's available to everyone, right? So the origin of this, right? I came from PODAT, right, the Physical Oceanography Data Center. So ocean science is actually something that's very important to me, and at that time, right? So we look at, obviously now we have all this hurricane happening in the ocean. People would pay more attention to the temperature of the ocean. But this is one simple analysis, right? And we talk about, back in 2016, 2015, that people would say, hey, can I just look at this data, and this is Hurricane Harvey, and this is right there in the coast of Louisiana. And can I quickly generate the time series and see how the precipitation and the interaction between the precipitation and also the sea surface temperature, right? Everybody knows how to do that in this room, by the way, because you just have to subset the data. You just do some, maybe IDL or MATLAB code to generate. But we want to do this on the fly, okay? And we can do with this solution. We actually expose this as a web platform. The user can just draw the box, and on the fly, we talk about seconds, right? Few seconds, we can compute this in parallel using our this open source solution and see that, hey, look at this, right? The interaction between the two different physical parameters. And if you also know anything about NASA, these data actually stores in two different archives, two different DACs. One is in Goddard, the other one is in at JPL. So how do you fuse them together and into one simple? And that gave us enough knowledge to build the solution for the NASA C-level change portal, which you all can look into, and release this tool called C-level data analysis tool, where you can overlay different parameter and see how generate time series and see how they interact with one another. So if you notice that the little box there I'm drawing, right? And then you have a time series on the bottom that actually has a little bar that actually moves. And what it does is that it gives you what we call interactive analytics, because the scientists can see the synchronization between the visualization and the analysis, and they can jump at any time in the plot to see something interesting. Most of the scientists I work with, right, they would just draw a location and say, give me the trend, and then they can home into certain area of interest. And this gives them really fast and quick access to the data. But because the solution is low bandwidth, right, all the computation is done on the big cloud in the back end, we were able to release a mobile version of the same tool. Low bandwidth, runs on your phone, doesn't require Wi-Fi. You can run on the cheap, we're talking about like, 3G network. This is when we first started was 3G network, right? But same analysis, same visualization, but just different platform, right? So talk about scalability, right? The portal back in a couple years ago, we released this tool for IPCC sea level projection tool, and I'm sure everybody read the IPCC report. When we released this tool, the world start hitting that server, our system, simultaneously. In less than 24 hours, we served over 135,000 people to our system from that one server, that one piece of data that we want to make available and analysis. We broke records. We broke IPCC's record for most active number of users served. We broke NASA record. They never seen that many users hitting our server at the same time. But that shows you scalability, right? So the open source solution we're building is really looking at not just say, well, yeah, we can do this fast, right? Can we really run everything in GPU? But that's too expensive. But can we run this in cheap computing environment, but within cost, right? With NASA, we have fixed costs, fixed budget. We don't get, the revenue. So I have to go cheap to figure out what is the best way to be able to answer this big data question, but still within the cost that they enable us to do. So we actually have another deployment. This is actually learning about how much water we have in California. This is looking at Central Valley. Central Valley in California is all farms, and people just drilling and digging waters, right? And guess what happened? The land is actually sinking because they pump too much water, right? So we actually have a tool that actually you can quickly drill into different in situ stations, this well data, and see how they're changing over time. So as I was preaching over lunch about open source, because the strategy for us is we open source this one analytic platform, is so that the community can actually deploy it and then run it for their data domain, but make it available through common API. So now the people in the middle, like a web application or Jupyter Notebook or some VR environment, can just stitch together, orchestrate these services. But somebody else is paying for the computations. And you don't have to do data wrangling anymore. And so we have been very successful. These are some of the deployment out there that you can connect to. So that's one area the AST has been looking at, right, over the last several years now. The other part the AST is looking at is actionable predictions, or a new observing strategy. Can we use science to drive and help us decide what is the next observation? What do we need to take in terms of, can we retest the instrument? Let's say we see a fire somewhere. Can we retest some of the instrument to take additional measurement for that location for a certain period of time, right? And it takes a while thinking. This is not just by can I fly a drone over somewhere, but think about being able to translate from data analysis to instrument planning, to ground data system, all the way to instrument uplink, to downlink, and all the way down back to data processing, and get it back to where data could be used by scientists. So that's the second thrust area the ASC is looking at, is being able to be more agile, right? So why am I talking about these two things? Because these are actually two of the very crucial building block for the digital twins architecture that I'm about to present. So people ask me, what is digital twin, right? And everybody, depends on who you ask, right? They might have a different view about Earth system digital twin. And in a nutshell, I see the Earth system digital twin is about past. This means what has been happening. This is about long-term records. What has been happening here? What's happening now, the present time, right? And then what are the future means, like scenario-based questions. What are some of the possible outcome, right? And what if you make some changes? What would the possible outcome might look like, right? That would be the future, right? So the Earth system design is really an attempt to try to address all three of these things, and which is, I think it's a little bit nuts, but it was kind of interesting when they first came out with the idea, right? But if you want to read the definition of Earth system digital twin, there's a whole website on there. It's under the NASA Earth Science Technology Office website /AST. And it'll give you the definition, right? Most people think about digital twins more about model, right? It's true, model is actually extremely important. You talk about like data assimilation or even ML, right, AI capability. But I just mentioned earlier, well, one thing you also need to have is long-term records, be able to see what's been happening in the past, but perhaps even learn from it. But more importantly is also being able to continue ingesting new data in real time, using that data to improve our next predictions, right? So now is a little closer to more operational environment now, because most of us who are doing research, technology research, or any kind of demonstration, we could sort of just cut a block of data and just focus on that block of data as like, there's one event and let me write a paper on it, right? But being able to create a system that's continue being improved by new data that's being onboarded or new observation, because I was sharing with some folks, right? Your model prediction is not the actual 100% prediction, right? You're not going to be able to predict the future 100%. So using the actual information can help you improve what your next prediction, because now you have some actual data to validate, well, how was my previous predictions? But the other thing that the AST Earth System Digital Twin definition want us to focus on is the what-if scenario-based questions. What if there's huge rainfall in this region? Where is this water going? What are the sensitivity area what might get flooded? What if there's a wildfire happening here? What are the emissions? With the wind speed or wind direction, where are the smoke will be going, right? You probably read all the news about the Canadian fire, right? It's kind of interesting. The fire started over here, right? Kind of north over here, but now it's like all over the East Coast, right? I actually have a slide about that. So as a computer scientist, in case you don't know, I'm not a computer scientist, I'm not a scientist. I'm a computer scientist. I've been building software for a living for forever. This is actually a real a software architecture challenge, building an Earth System Twin, right? Because you try to connect all these capabilities together. First, you're going to have the analytic collaborative framework, which is have a way that you can bring this data where you can optimally analyze and visualize this data. You have to have a way to be able to acquire new measurement that's including retasking instrument, but could be acquiring new observation or just pulling some new in situ measurements somewhere, right? AI, which is extremely important, is not just about predicting some model output. AI is actually crucial when you deal with big data. You have to be using AI to help you be more effective in terms of running operation. Where should I prioritize my jobs? What are the relevant data we should be incorporating in the next run, right? Helping us to be more cost effective instead of just looking at what the next plot looks like. It has to be real time, means that whatever the latest data, I'm not talking about, not all the data is going to be at real time for us because we are heavily dependent on what data is available, right? But real time means as soon as it's available to the public, we want to get it in there, right? But it has to be federated because, as far as I know, no one can build a complete replica of the world, and I don't think I will see somebody can do that to the level of accuracy, right? So it has to be federated where you are able to leverage some data from different people, different organizations, some experts, right? This is why the whole idea about creating a community is extremely important. Multi-computing, right? Not everything has to be done on the cloud. Not everything has to be done on the GPU. There are models that actually runs a lot better on the HPC, like Wharf model, right? Well, your digital twin has to be able to take advantage of those things instead of trying to get everybody to say, well, let's put everything on the cloud. Do you know how much it costs to move a Fortran model to a cloud and be able to run it effectively and and without bugs? That's silly, right? So the architecture has to be able to connect to these digital goods that are mature. Somebody already running this stuff. Why I have to replicate this thing, right? It of course has to be multivariate, but it's also support different resolutions. This is why when I said federated digital twin is important, because you might have a global digital twin that tells you where our sensitivity might happening, but you might have to connect to a regional digital twin that they might connect with some of the regional data that you don't have and we don't have in NASA, right? Population data, or even some local sensor data that the city's been deploying that you don't have access to, right? So think about federated architecture where you have a global resolution data, but then you get to a regional resolution where you can see things like in the street level, right? That's quite interesting, right? Because you try to build all that into one big system, it's going to be, again, too expensive to maintain. It has to be visual, it has to support visualizations, And again, we also talk about assimilation and numerical models. So all that has to be considered as a framework. So we started this work actually through my collaboration with the French Space Agency, looking at flood. And we piggybacked with the flood project because JPL and CNES is working on this mission called SWAT, right? So hey, perfect, right? We can actually create something that we can potentially use the SWAT data, right, in the future to look at actual flood or sea level. So this is actually a software architectural diagram that try to put a digital twin into something that people can fully understand. Like first of all, the blue area is the physical world, and the yellow area is the digital representation. And then you will see the outer ring, and these are the key players of a digital twin. Right, first one you will have is the actual ACF environment or Analytic Collaborative Framework. This is where you bring all the data, model outputs, and observation into one place where it's optimized for analysis and visualizations. And then you use that to drive your assimilation numerical model and also to train your ML models, right? The output of these is really help us predict what might happen, but that also more importantly drive to our next thing, and this is where you bridge to the physical world, is about actionable, right? Things that decision maker can look at. Could be, changing the routing time or what time the truck take off or move out of the port to reduce pollution in the street, right, on the highway, right? That's something, the actionable decision that they can do. But the other decision that they could do is, for us, is like, well, we don't have enough data. Let's pull more information from these local sensors and regions, right, in situ data, or that we can actually now have a much better picture. Or more go even further is be able to, if you have instrument that's orbiting the Earth, you can actually retask the instrument to acquire additional observation, and that information staging some data access environment that you can actually bring into the ACF again. Now your ACF have more newer data, and you can continue to improve and your next predictions. And that's basically, for me, is what we call, we branded this solution called Integrated Digital Earth Analysis System, or IDEAS, as a framework. It's not a one-off just for flood. Also, we built this framework as a platform-based solution. Means that it connects different technology solutions together, do common APIs. They could be running on different environments, but you're using standards like OGC standards or like things like Stack or OpenSearch, right, to access the system without having to take a cloud class, right? So I share this a lot, right? It's like, people like to talk a lot about clouds. Like, look at, I do this with Object Store. I did this with CloudFormation. It's like, awesome, that's fantastic. But when I signed up for my Gmail account, I didn't have to take a cloud class. So I want people to use my digital twin not having to take a cloud class, right? Unless they want to integrate something, then it's their choice. But we are using common interfaces, and it's also, you could connect to this digital twin using any programming language. So you're not requiring your scientists to learn about, how to do everything in Python. You should be able to connect to the system using Fortran, as long as you can use HTTP connections, right? So the first application of this digital twin framework is the hydrology or flood detection prediction solution that we're working on. This is actually in partnership between NASA and with the CNES based, the French Space Agency, but they're funded through the Space for Climate Observatory consortium, and so it's quite interesting because they are building an effort called Flood Dam, and it's looking at building sort of digital twin model to estimate the water level and try to use that to connect with some commercial information to see how much, what's the risk, financial risk might look like. So they look at that part of the equation. But on the NASA side, we look at, hey, we have a bunch of models that actually can simulate the water, figure out where the water is going, right? So can we build that and connect these two digital twins together? And this is actually our first example of federated digital twin, means having two digital twins be able to exchange information, right? So it's a pretty large team, right? So I'm the PI for the NASA side, and and definitely have the privilege of working with the Goddard Space Agency and also Flight Center, and also with the Langley. So again, it's two digital twins connecting with one another. They each bring the digital goods. We bring our NASA digital goods and our model, and the French side, they bring their own satellite and also in situ measurement. And the other part that the French side also has is they actually have IoT devices. So they actually have smart instruments that actually mounted under the bridges that they can take live pictures and measurement, and we can connect to it directly. Right? That's kind of fun to try to, as a use case, to figure out how to dynamically acquire these in situ measurements. So besides NASA and CNES, there's definitely several other organizations are on this project. So to put all this together, right? And again, I'm not a scientist, so I learned this as I'm developing the system by working with some of the very, very smart scientists, right? So to look at flood, right? You want to have a model that actually is looking at the runoff, right? So when it rains, water runs off, either the surface runoff or subsurface runoff. So that can tell us where the water, where the water is heading. But then you would also have actual discharge model that actually tell you the stream. So when you have this much water going to the stream, based on the topography and the river network, where are the sensitivities? And so that's the second model, right? Once you have the discharge information, you can pass the information to the French side. Now they can figure out how much the water height looks like, the elevations, okay? And by having the elevation, we can pull in the IoT measurement and now look at the actuals. Okay, that's connecting all the pieces working together, having three models kind of connecting and two digital twins. But more importantly, being as a digital twins, we all know that one model is not enough for any kind of use cases, right? So we actually have multiple surface runoff model. So the one that's showing here is the one that actually run on Goddard and in the HPC environment under the LIS or Land Information System, right? But we also pull in 3 other land surface model. So now imagine being able to run this using 4 different land surface inputs to this one discharge model. Now you have different variety of possibility that you can look at, okay? So that's the big picture, right? So we're using the French Garonne River as one use case, but we're also using the Mississippi Basin on the US side for our use case. So that's how to connect all these things together with our digital twin. But the other part about being digital twin is being able to ask what if questions. What if you have certain amount of rainfall, right? Let's say you start with nominal amount of precipitation, where the surface runoff look like, okay? What happens if you double that? Okay, what happens if you triple that, right? And now we have this. Now it's become more interesting because now you can start looking at different scenario, and the city planner and the people living in the flood plain, right? They can actually start looking at, well, yeah, these are possible scenarios that this digital twin can help us to identify. So that's one of the things that we built into the system. And people like to use ML a lot. And besides looking at resource planning, which is very important, is one of the things that we also look at is, can we use ML to tell us which in situ sensors data we should bring in? So those of you who work on in situ data, right, you know that's just way too much data. Some of them are actually really high time resolution, like 5 minutes intervals, right? You want to bring all that in just in case somebody uses it. That's just too much data, right? But what if you have an ML model based on the precipitation and the runoff, you can predict that these are the sensitivity area, and we can just pull just those in situ sensor data into the system instead of having to bring everything in at once, right? That's the part about being smart with data instead of try to, bring it in case somebody will use it, right? So that's capability that's into this in our flood digital twin. Something recently we added. Tom, you've done this? So you thought you're just doing with ocean stuff. We took the technology that you guys developed over that ocean matchup capability, and we actually got it to work on for flood. So this is actually a matchup, right? Between the precipitation and also the runoff, and we do this on the fly, right? So that's the thing that you guys built, right, in your Access project, is be able to do this kind of on the fly matchup between satellite to satellite, in situ to satellite kind of use case. So now it's available to our digital twin. It's open, and there's a notebook that you can download to use it. By the way, all the links is in my slide, and then you definitely have a copy to look at those, play with those notebooks. They are open to the public. You don't need an account for it. So we have notebooks. Again, you can actually generate visualization within the notebook. The reason we actually open this notebook is actually we can work with our French partners. Right? A big open source advocate. We also open our platform so that anyone can connect to it, so they don't need to get an account in our system. And then to help them integrate, we give them a notebook that actually basically documents APIs that with working examples. So this is you're looking at the Hurricane Ian there, right? We can generate the visualization of Hurricane Ian when it heavily saturated Florida, right? But you can look at all the analysis and data there, and at the French side, they basically using this as a way to figure out how to pull the data into their system. And you can play with it too. Again, it's open to the public, right? So that's cool, right? You have a platform. You can actually run some data analysis with notebooks. We got, the next thing we did is, why not just build VR on top of that, right? And that's what we did, right? So because when I was looking at digital twin, is a harmonized environment with satellite, model, and in situ or subsurface measurement, right? This VR environment is a full immersive 3-dimensional environment. It's a perfect environment where you can actually bring all this together in a way that's actually easy to work with. And then you have infinite workspace to stack these data together, right? So it's built on top of the same platform, same digital twin that you just use the notebook that I just showed you, but now you have a VR application that you can talk to the same system, right? So in this case here, you're looking at some of the discharge information, the runoff in a fully immersive environment, right? And yeah, so again, no replication, same platform, same. It doesn't cost me anymore because I already paid for the platform, so, right? So it's all about keeping up to date, right? Of course, recently there's flood event happening in South Korea where it ended up what happened, right? People got trapped in the tunnel. The tunnel got flooded and people drowned in the tunnel, right? We were able to quickly pull in the precipitation information. We also pull in the soil moisture data from SMAP mission, and we can actually generate the analysis to look at how saturated is the ground over there. So this is what we did with flood, right? The next thing we're using this digital twin is actually creating a wildfire or wildland fire digital twin relate to air quality and impact. And this is a completely different group of people I'm working with. So I have the privilege of working with the deputy mayors of Los Angeles, that she could consider herself as a stakeholder because she wanted to use this thing to help make her decisions, right? But we also work with different universities to basically looking at, we start with just understanding air quality, but then now we start to connect this with wildfire because California is this kind of wildfire capital, sort of, right? So it's just kind of important to me too. So so when we work with the mayor, deputy mayor, right, she kind of set the bar high, right? It's like she wanted to say, hey, I want to be able to characterize and understanding and improve the quality of air that in the urban area across this planet, right? That's pretty high goal. But we would use Los Angeles as our test case here, right? So we're using, so when we started off, this was supposed to be just an ACF effort, means that just have all the data in one place so we can quickly look at it. And then we built some ML capability to predict what the PM 2.5 looked like for the next day. That was starting, right? So, but then we started formalizing that into a digital twin architecture, same architecture as before, or framework, but now you plug in with different model, different data, okay? Using the same interface, same API, but you just work with different kind of data, right? And we start off with the long records, right? So recently I gave a talk at the NASA Hybrid Wall, right? And we actually using like one of the instrument OMI. I'm sure some of you already know about OMI. It's been flying since 2005, and having long-term records actually kind of help us seeing what's going on. Are we making a difference in terms of all the policies, for example, right? So this is actually looking at measurement of NO2 and SO2 between 2005 and 2022. This is over in Ohio River Basin, and you can see that definitely there's a downward trend, right? This is actually means that things are improving at least in the U.S. region, right? And to look at for China is very similar case, right? You would actually have some reductions. Actually 90% of SO2 reductions. That was quite good. And as you probably know, China probably, early days, they didn't have a very strong policy in terms of pollution. So, but India has got it interesting as well, right? You look at 2005, 2022, there's some little hiccup there. But it's also interesting to look at this plot, right? There's a drop. Both of these drop at the same time in 2020. Guess what happened in 2020? Everybody stay home. COVID, right? So that, to me, this is actually a real story that shows that human activity does have impact to the environment right there, right? It doesn't take a PhD to understand this. But you also notice that, after the when we come out of the COVID, they start climbing back up again, but we do see some improvement in India after that. So that's pretty cool. So this is what I'm talking about in terms of long-term records. So we know what we can look at the charts and say, okay, what is attributed to these, increase or decrease. So recently, right, NASA has definitely relaunched the Temple, right? You've probably been tracking the Temple satellite. It's a geostationary satellite that focuses on North America regions, but also the reason why you want to do it geostationary is because then we can actually be able to gather measurement at an hourly basis, right? Instead of waiting for like the next 24 hours, what's going on, right? So, and of course, South Korea is doing the same. They actually had the JAM satellite doing the similar focus in their region. And then you have the Sentinels, right? So we call this a virtual constellation. It's like, instead of having one big satellite that does it all, can we create a community that the satellite that we can connect them together? So we established this, what we call the Air Quality Information Center, right? It's the one platform that for all the measurements and satellite model and institute, and also be able to also try to work with a real mission like Maya. So the Maya mission, which is will be launching in a few years, has a retaskable camera. So we want to see, can we build a simulation where simulating retasking the instrument of that, right? Well, because we're working closely with the science team there. So the goal is creating an integrated observing system where you get data from the satellite, from airborne, from the in situ measurement, right, and even medical devices, in one place. So our platform, we were able to, because we continue keeping up to date with the latest data, we were able to track the Canadian wildfire, right? These are animation that you can generate directly from this digital twin. Different compositions, right? Different species. You have the carbon monoxide, you have the NO2, you have the observation that we gather from years. But more importantly, you can actually see that pulling the measurement directly over the ground of New York City and see what people actually, what's the PM 2.5 looks like, okay, into our system, and start looking at, compare that with satellite and also now on ground. Of course, we started this project by putting an instrument on top of one of our JPL building, and those of you who've been to JPL, like Doug did, we know it's right next to the Rose Bowl, right? Every July 4th, we have fireworks. And we actually was able to gather this instrument that we attached on top of the building. We were able to measure the black carbon as a result of the fireworks. and we pull this data into our system live, okay? And I kind of jokingly, but I put this instrument on top of my manager's building. I just told him that I care about what you breathe, so I put the instrument on top of your building, okay? And of course, Tom, I would reuse everything that we can, right? So we also deploy a matchup capability that you helped develop for air quality and wildfire. And this is where we're doing a matchup between the viewers and modus on the CISL optical depth, right? So 2 different instruments. We do this on the fly. And it was, the software that you guys developed, it was so robust, right? It took our engineer only like 2 days to get this thing integrated. It was like awesome. And like now it's a new service for matchup. So now you can do CalVal if you want to. Okay, so latest additions we added to this air quality system. We want to tackle things like greenhouse gas, right? So so recently, and this is what I'm talking about recently, like as of early this week, we onboarded CO2 data into our system. This is an actual observation that gathered through the OCO3 mission. What is different in this one is that in our platform, we already have a notion of what we call analysis-ready data, but everybody knows analysis-ready data is just a blanket term of different formats, right? You have things like Parquet, you have things like ZAR, you have like COD, right? So, but we create a platform where nobody cares what ARD is. So you need to use, as long as this data is stored optimally for analysis. But in this case, what we did is we created a pipeline where we take the OCO2 data, OCO3 data, and transform them into ZAR tile and store them into cloud optimized, object store. And using the same platform, the user let me look at what the CO2 concentrations over Los Angeles, and we can do this on the fly. So this is new because now we can start supporting things like greenhouse gas analysis. And just for kicks, one of the things why we're tracking greenhouse gas emission is we really want to monitor some of these major fossil fuel power plants, right? So one of the paper that we actually look at this paper, we try to replicate the entire analysis from that paper. This paper actually tried to study the largest fossil fuel power plant, and that's in Poland, right? And see if they actually really emitting according to what they expect, right? So a lot of times you would suspect that they would actually report the emissions, right? But now we actually have the actual gathering of the CO2 from the sky, and now we can compare how close is are they lying or not, right? But you also look at actually I forgot to mention here, is that you also see some of the drop in CO2 in 2020 because of the lockdown as well. So the digital twins is still being built, right? Both of these, right? But the air quality ones, right? We actually have more bells and whistles. So we actually have a GIS-based application. We also able to generate daily prediction of PM 2.5 for Los Angeles. We're also adding things like NO2 in there. And we generate animations of the actual, now people can visualize where these things are traveling. Of course, we have the VR capability, and also we release everything as Jupyter Notebook for helping educating people and also for integrations, right? So you can go to the website, which is, I'm sure Christian will share the slides with the links in there. You can play with this tool. This is actually an example of how we combining looking at the Canadian smoke of the fire over in the east, analyzing the smoke over in the East Coast, where you look at the in situ measurement over and also the satellite observation there. And I mentioned before, we also use the same solution. Now we can visualize air quality measurement in 3-dimensional space. Things that we still have not worked on is building out the scenario-based questions, right? So I kind of mentioned this, my sponsor in NASA headquarters, right? I love working with her. She's awesome, right? She just told us, I want the Tony Spark experience, right? It's like be able to put these things together, right? So we want to build that, right? That's sort of like, okay, I get it. So we'll build something like that, right? So we're working toward that what-if scenario. So again, Maya is a satellite that will be launching in 2025, and we are partnering with them, really just focusing on they are collecting measurement like PM and looking at human health. The goal is really try to, now we have one place for looking at, can we have enough information in this digital twin to look at what is the cause and effect and also health impact information, right? So everything I talk about is open source. So Tom actually helped on this too, right? We released this book about a year ago. It's the big data book that talk about the open source ACF solution that we created, but it's also the matchup capability I just presented is in that book, right? Recently, I was interviewed by AMS about the book. There's going to be another article coming out from Science magazine about this work, and the goal is really try to open source a solution, but engaging standard community like OGC and GEOs and NIH, why you want to build a community, right, to buy in, and then help them use their case to help you define and refine your standard. Okay, so that's why I've been traveling quite a bit to work with different people with different backgrounds. Final slide, right? If you want to go far, just go together, right? So I think people like to build digital twins. I would just share over lunch, like the different people are building different digital twins, like in Europe. I'm really happy to see that NCAR is already thinking about that too. Go ahead, don't like go just because we build one and say, well, they already built something. You have your digital good, right? Go ahead and build your digital twins, but looking at how to create interoperability, right? Because you have digital good that I don't have, right? So how do you make them? Can you create a community of digital twin that you can actually orchestrate together? And now you might have a much closer representation of the Earth rather than try to think maybe NASA will build something like that. No, I don't think we can build it. But my goal is try to create a reusable framework where it can bring the community together. Okay, so with that, I stop my talk, and this is my email if you want to talk more.
Okay. Thanks, Thomas. Do we have any questions for Thomas in the audience here, or is there anything online, Kristen?
Wow, speechless. That's the question there.
Hi. I am just wondering about interoperability in terms of exchanging the data between the different digital twins.
Mm-hmm.
As I know, there are some format out there, they are trying to make some kinds of a standard, for example, OST.
Mm-hmm.
Is there any plan to, because there are lots of different data formats, so
right.
Maybe somebody wants to log into your system, export data in a common format, and then ingest it in their digital twin or something like that, and use it over there.
Right.
So is there any plan to?
Yeah. So we actually touched a little bit in that area. First of all, the front end to the system is all RESTful based, right? So if you can ask the subset of the data, it's going to come back in the JSON document, which is probably not something that scientists would like to use, but it's portable, right? So you can subset the system, and we can give you in JSON, but you can also ask the system to subset it and give it to me in like CF compliant CDF, right? So that's one of the things that the matchup team is actually looking at, right? So we do want to get to the point where be able to support variety of standard for interoperable. But also another thing we want to think about is the goal is try to keep the data in place, and so that we can give you the analysis is much more cost effective. It's much more easier instead of having you to download the file. Because one of the requirements for digital twins, we also retain the lineage to the original data. So like a lot of the data we pull from the NASA archive, the Earth data, right? So we can actually point you, say, where did you get this data from? We can still point you back to the granule, right? So there are a couple options for pointing you back to the original source, but in the system, we can also provide different options for you to do subsetting. So Yes, definitely. And I think the CDMS team is also looking at standardization, some of that as well. So, cool.
I was curious for some of the live demos you're showing, like your C-level ones in the beginning. How much server-side infrastructure is required to support that to scale to lots of users, and how much is done client-side?
Great questions. The system was so robust that the backend, with 175,000, we didn't actually have to spend a dollar more than nominal. It was pretty fantastic use case. What we actually end up having issue was the web server side, which couldn't keep up with the request, and they just have to make some changes to that because they didn't expect to have that many people coming in. But the user, nothing. Again, the point is that we don't want to levy too much of fat client on our end, right? We will provide the result, but the user have the option to do fat client. Like the VR, I would consider VR as a fat client, but for the rendering purposes, not about analyzing our data, right? So, and this is why I'm so why I want to share the C-level stuff early, because it's a very good use case where the software engineering team, we spend the time to making sure that the operation of the system is cost effective. It doesn't just go out of scaling and start allocating more virtual machines, because that's where it's going to burn our budget. The C-level portal doesn't have a lot of budgets, right? So that's why we have to watch. While it's very popular website, we don't have a huge budget to work with in terms of keeping the things running. So we want to be cheap. So the same number of machines is still the same with 135 people hitting it at the same time. I was very proud of that. So,
yeah, another kind of follow-up question related to, I guess, like all these different sources of expertise are having to talk to each other to make like a VR client versus a web client versus like running the actual like the AI models. How are you, I guess, from an organizational perspective, how are you orchestrating like the different teams so that one team is producing something that like even before you get to your different users around the world? How have you managed a JPL to get these different groups to work together to make things more interoperable?
Yes, great question. So I'm very fortunate that the people who build this technology are in the same section. They're under different group of our section. So we are sort of having a mutual understanding how to develop the software. But we definitely have different expertise, right? The VR people, right? They have what they need to know is that, well, how do I access to your system? What are the APIs, right? Once I know how to access your system, the rest of like doing the polygon stuff is my domain. The web person, right? And she's looking at the whole JavaScript and application, and that's also another open source software, by the way. It's called Common Mapping Client. And what she care about is what are the API I need to know to load the layers, the image layers, and what are the metadata for each data set, like time ranges that I can query, right? But these are all captured through the notebook example, right? So we're actually using a notebook as a way to share to the team, like how to integrate with our system.
Well, thank you.
We do have some online questions, so I'll read one right now from Nihant. What are some data visualization challenges and/or opportunities that you see while working in the digital twin framework?
What are some of the challenges? I couldn't get a scientist to wear goggles yet. So the next thing we are looking at, and this is something I'm looking at, is ARs, right? Augmented reality. So, but in terms of the environment, because then they don't have to use goggles, right? They can actually use your phone to do ARs. So we try to provide different way for the scientists to look at the same data. But the other challenge is having to looking at the different type of data over time. They are different, right? It's not as easy as just these are raster data, these are in situ data. Some of these are very different, like the CO2 data, right? They actually is, if you look at the data, it's not a global coverage. They actually have different spots in the area. So how do you make that display and visualization, but also the tool allow the user to navigate between these what they call SAMs, right? And still make sense to them. But that is very tailoring, right? So you have to tailor the tool for that kind of data, right? So don't get me wrong, right? When you're giving a framework, it doesn't solve all the science problem yet, right? There's always some kind of tailoring involved because your community and your data will have their own different characteristics. So there are some tailoring involved for different disciplines, right? So learning their specific visualization, learning their expectation, their community is also hard. This is why in my team, besides engineers, my project team, I also have at least one senior scientist on the authority on the data, but I also have a science system engineer. So science system engineer is like the glue or liaison between the engineering team and the senior scientists. They know a little bit technology, communication, but they also got the science background to communicate. And so that liaisons actually really help understanding or digest what the senior scientists want, and guide our engineering team. So I think the visualization, one of the other ones is, besides the whole gargle thing, is really try to understand the local expectation and nomenclature. And this is why when we build the VR or building any kind of visualization, instead of say, what do you want, which is a user bad idea, is I would ask them, what kind of tool you guys been using over time? Can you share with me with some of your publications? Did you give any presentation on the work that you have done? And using their presentation, they usually have some graphics there, right? So then we can use that to help guide the visualization team. So, oh, there's one more question there.
Have you given any thought about ingesting data of different pedigrees? Like, for example, we've been approached very recently by the University of Hawaii. They want to deploy a bunch of sensors in very close density to like the Maui Flyers to get very regionalized air quality measurements for local community concerns.
Yeah.
And they may not be research quality pedigree data sets that you don't necessarily want to leak into global world availability, but they're still open and timely. Any thoughts or ideas about how that could be implemented in the current framework?
Well, I mean, the framework itself is, well, we designed the framework to bring in whatever data is available, including campaigns, right? So this is very similar to a campaign, right? We can just, we're doing ICOAD already. So yes, so we definitely can bring in different pedigree of data in there. Now, the second question about that is about accuracy, right? And that is a little hard one, right? So this is why you need capability like matchup, right? To do the calibration to see. But another thing we can look at is, are there nearby ground sensors like AirNow or Purple Air sensor that we can actually pull in to see calibrate. Yeah, we learned this, that we don't just take the data just because the machine tells us the data. That's that number. Initially we actually calibrate by looking at the nearby sensor that we know we used before as well. So yes, we definitely can support campaign data. So.
I'll read one more question from the online audience. This is from Negan. Thanks so much for the great presentation. This is fantastic. Are the codes for these demos available online? If so, can you please point us to the repositories? Is there a centralized place to put your infrastructure, VR, visualization, ML codes? And then it looks like Negan found the GitHub repository, but that it only included notebooks.
Okay, so yes, they are all open source. So my email, write down, send me an email. I'll send you all the links. Yeah, we get that question a lot too. And because again, working with NASA, right, we are all for open source, open science. So if they have not been open source, they will be in open source shortly. Part of that, we do have to jump through some hoops organizationally to get in there. But for somebody who's been doing this for 20 years, right, I don't own any software in my secret pockets. So.
All right. Thanks again to Thomas
Yeah.
for speaking today and joining us, and thanks to the audience.
Thanks for having me.